Algebra Lesson 3-1. Today we're going to first start looking at solving equations. And one of the main things we have to do when we solve an equation is we have to think about inverse operations. Now, operations that we would typically do are multiplication, addition, division, and subtraction. Those are some of the basic operations. And an inverse is sort of like saying an opposite, and that's like the opposite of each one of those main operations. So the opposite of addition would be subtraction, the opposite of subtraction would be addition, and so on with multiplication and division. So they are operations that will undo each other. They help us to do what we're trying to do when we solve for an equation, is we're trying to isolate a variable. If we're solving for r, we want to get r completely alone. If we're solving for x, we want to get x completely alone. The idea behind solving equations is to play what I call a shuffling game using these inverse operations to move stuff from one side of an equation to the other until we get the desired variable alone. That's what we would like to do. So it takes some practice, but it's really just kind of a game. As long as you know the rules, then you can do the game. You can play the game and be successful. Each time that we use one of these inverse operations, we would call that a transformation. We're changing the appearance of the problem, so we're transforming it and allowing us to solve. We would call each one of those steps a solution step. So we're showing step by step by step what we're doing. We are not going to be jumping to any solutions, no matter how easy it may seem. We need to practice solving on the very basic and easy equations before we're going to be able to apply all those steps to the larger, more difficult equations. So these solution steps are very important. A transformation, we talked about this a moment ago, saying it changes the appearance of the equation. Adding to each side would be considered a transformation. Subtracting from each side would be considered a transformation. Anytime you simplify, you're changing the appearance of the problem. Interchanging, so you're taking one side and rotating it around to the other. Anything like that, and there's more on page 132, but we're going to go through some of them now. That would be considered a transformation. So if you had, for example, 5 plus b is equal to 12, and on this side you add -5, you can't do this add -5 unless you also do it to the other side. It has to be fair. You have to keep things fair. So whatever you do to one side, you must do to the other. This would be considered adding to each side. If I only add it to one side, it won't be fair. Think of the equations as balance scales. They're perfectly balanced, means they're equal. If you were to have b plus 5 on one side and 12 on the other, and I say they're equal, that means they're balanced. The moment I add something to one side, it becomes heavier, which means they're no longer balanced. Well, if I add something to this side, I'd have to add the exact same amount over here to balance it back out. If I take something away from one side, it's going to make it lighter, and thus the other side would go down. The only way to balance it out is if I take the exact same value away. So whatever we do to one side, we must do to the other. So that's an example of what I mean by adding to each side. Alright, now, the equations that we're dealing with are considered linear. And if you look at linear, and I go like this, and I kind of just cross out the AR, you should see the word line. Linear equations will form straight lines, and we'll get to that later on, but I just wanted to make sure you notice that. Think of linear as straight. They are going to have a variable in them, but it's going to be raised to the first power, which means you may not even see the exponent at all. Raising something to the first power is just to the power of 1, and we typically don't even write it. You're not going to have the variable in the denominator. You're not going to have a variable inside the radical, the square root sign, and you will not have a variable inside the absolute value brackets. So for example, we might say y equals 2x plus 4. This would be acceptable because in reality, it fits all the descriptions of a linear equation. Yeah, there is an exponent of 1, even though we don't typically write it, but there is no variable in the denominator. We have no variable inside a radical, and we have no variable inside a bracket, absolute value bracket. So this would be a good linear equation. These would not be linear. Just as a couple examples, not linear. Y equals the absolute value of x. That would not be a linear equation because the variable's inside the bracket. Y equals the square root of x. That would not be okay. Y equals 14 over x. So those would not be what we would consider to be linear. Or y equals x squared. Because now you have an exponent of 2, and that's not allowed. Alright, so these are some definitions about what a linear equation is, what we're going to be dealing with to solve. This is the idea of what you do to one thing, you must do to the other, or to keep things transforming, changing the appearance, but not changing the value of an equation, just how the equation looks. And each step that we use is called a solution step, and we'll be using inverse operations. Now, I like to think of the inverse operations as something like this. Say I'm starting at the number 0, and I take and I add 5. So if I add 5, now I've stepped here. If I take that value, and then, which I'm now at 5, and then I multiply it by 4. If I multiply that 5 by 4, I'm now at 20. So I've changed my location. I was at 0, I added 5, I multiplied by 4. The only way I'm going to get back to that exact same spot is if I undo everything that I've done currently. So instead of multiplying by 4, I would divide that 20 by 4, which would put me back at the 5. And then instead of adding 5, I would subtract 5 to put me back at 0. Those are inverse operations. I'm undoing everything and going back to the start. So here are some basic equations. Very simple. I will make some modifications to their appearance because I like to practice changing subtraction into addition of the opposite. Not everybody needs this, but I have found that most people make fewer mistakes if they make these adaptations. Now right now, there's an x on the same side as the 9, there's an equal sign, and there's a negative 17. You must think of this as two sides. Remember the balance pans I talked about? Right now, the balance pans are perfectly balanced so that this side is equal to that side. If I take something away from this side, it's going to change the balance. So the only way I can be fair is whatever I do to one side, I must do to the other. So I'm going to change from minus 9 to plus negative 9. I have not done anything as far as the balancing is concerned. I've just changed from a subtraction problem into an addition problem. Now, we want to isolate a variable. We said we want to get a variable all by itself. That's what isolate means, which means that's the variable I'd like to get alone. In order to get this variable alone, I've got to get rid of negative 9. Here's where the opposite comes into play. What would you need to get rid of a negative 9? You would need a positive 9. So I add positive 9 here, and whatever I do to one side of the equal sign, I must do to the other side. So I'm keeping things balanced, keeping things fair. Now, these cancel out. A negative 9 and a positive 9 are opposites. I have the x all alone, which is what I would like, and I have an addition of a positive and a negative number. So I ask myself, do I have more positives or do I have more negatives? I have more negatives. The second question, how many more? I have 8 more negatives. The answer is negative 8. The greatest thing about solving these is you can test your answer. Take your answer and mentally plug it back in. If you add a negative 8 and you added negative 9, negatives plus negatives makes more negatives. So negative 8 plus negative 9 would make negative 17. This number actually works when we plug it back in for the variable. That's how I know it's a right answer. This plus 9 in green would be considered the solution step. And I'm using inverse operations because the positive 9 is opposite of the negative 9. So, again, this is just one example. Okay, a very common mistake here. If people don't watch their signs on this particular problem, a very common mistake is someone goes, well, I'm going to add 2. So they come over here and they add 2, which is the right idea. Whatever you do to one, you want to do to the other. But then they come up with, well, that becomes negative 9. If you plug negative 9 in here for n, negative 9 minus negative 2 is not going to make negative 11. Negative 9 plus negative 2 would make negative 11, but not negative 9 minus. So something is amiss here. This is why I'm a big fan of changing all subtraction into adding the opposite. Because now that that's really n plus 2, you would not add 2 to both sides, because adding a 2 is not the opposite of a positive 2. I can't add positive 2. I have to add negative 2. Now that positive 2 and this negative 2 are opposites. They will cancel each other out, which is perfect. Whatever I do to one side, I must do to the other. And I now have a negative plus a negative, which makes more negatives. And if I would like to test my answer out, I can take this answer and I can plug it in. Now if you try it, negative 13 plus a positive 2, I have 11 more negatives than I do the positives, so we know that works. Again, you don't have to make that change, but people make far fewer mistakes when they switch the subtraction. Alright? We would like to isolate this variable, get it all by itself. Right now, there's a 5 being added on to the x. The opposite of adding 5 would be to subtract 5. So I could subtract 5 from both sides. And this is totally fine. That 5 and this negative 5 are opposites of each other. They will cancel out, which means the x is alone. Here's the problem though. People make all kinds of mistakes with this negative 3 and this negative 5. They get any answer from positive 2 to negative 2. Unfortunately, both of those are wrong. If you do as I've been talking about, and you do adding the opposite instead of subtracting, the opposite of this positive 5 is to add a negative 5. They're still going to cancel out like before. 5 plus negative 5 makes 0. They're opposites. And whatever you do to one side, you must do to the other. Now you see you have a negative plus a negative, which means you're going to get more negatives. You get a final answer of x equals negative 8. That's way different than either positive 2 or negative 2, which is a very typical mistake when someone doesn't watch their signs right here. I'm just a very large advocate for changing subtraction into addition of the opposite. Test it out and plug it back in. If you added 5 plus a negative 8, you would find that you had more negatives. The question is how many more? 3 more negatives. So that answer works when it's plugged in. Alright, one more problem. 4 minus n equals 3. Now this one causes people headaches all the time. Biggest here, I'm going to do this incorrectly so you can see. The typical logic that people make is they see the subtraction sign and then they say, well, the opposite of subtracting is to add. So I'm going to add 4 to both sides. And then they have this and they say n equals 7. Well, if you test that out, if you stick that 7 right back in here, I don't think 4 minus 7 makes 3. 4 minus 7 makes negative 3. So this didn't work. So you might say, well, what's the problem? The problem is, this was a positive 4. So you didn't cancel it out. You actually made it larger. That doesn't solve your problem for you. You've got to get rid of a positive 4 in order for this to work. Now, I'll give you a hint. I'll give you a clue. Something that you might think about. You can change this to plus negative. It just means it's the opposite of n. So when we solve, we're going to get the opposite of n is equal to a number, which is easy in the end, and I'll talk about that. Now you want to get rid of a positive 4. To get rid of a positive 4 means you could add a negative 4. And that's fine. So go ahead over here and add negative 4. Now when you add those, you end up with this negative n is equal to 3 plus negative 4 means there's more negatives than positives. There's one more. So you might say, okay, I'm finished. But we're not finished. This is what the opposite of n is equal to. The opposite, or negative of n, is equal to negative 1. So what would just the regular positive n equal? But if you change the sign on one side, you got to change the sign on the other, so it would be positive 1. Now let's test it out. Take that answer, plug it back in. If in fact you write 4 plus negative 1 equals 3, it works. Or even 4 minus 1 equals 3, it works. But I'm telling you, watching your signs is extremely important. Now look at the difference between this. This says 4 minus n, whereas in the past we had a number, or excuse me, a variable minus a number. So this option A, this example A, is different than the example D, because here it's the number minus the variable. And that's the one that causes people the most difficulty. So please be cautious. These steps, these solution steps, you need to show them, because these are very simple one-step problems. We will get to problems that are much more complicated and require many more steps. If you can't do a one-step problem with this kind of work shown, there's no way you're going to be able to do a multi-step problem. You've got to practice these. It takes some practice. Once you get the hang of it, the game, I call it the shuffling game, because you're moving stuff from one side to the other. Once you get used to the shuffling game, the rest of solving becomes a breeze.